Welcome to our exploration of flight adaptations in avies. Imagine trying to build a flying machine from scratch in your backyard. You would quickly realize that your machine needs to be incredibly light, perfectly shaped to cut through the air, and powerful enough to lift itself off the ground. Birds are nature's ultimate flying machines, perfectly engineered over millions of years to conquer the skies. Today, we're going to uncover the brilliant biological engineering that makes this possible, from hollow bones to specialized lungs. To begin our journey, let us look at the external shape of a bird. Why is the ability to fly so crucial? Flight opens up an entirely new three-dimensional world, allowing birds to escape terrestrial predators, access new food sources, and migrate thousands of miles. To achieve this, a bird has a streamlined, spindle-shaped body that offers minimal resistance to the wind, much like the sleek fuselage of an airplane. Their forelimbs have evolved into wings, and they have developed specialized epidermal structures called feathers. These feathers are not just for show. They provide the essential aerodynamic surfaces needed for lift and thrust, while also insulating the bird's body to maintain the high temperatures required for the intense metabolism of flight. Now that we understand their external shape, let us look under the hood at their internal anatomy. A bird's internal structure follows the exact same principle as a sports car, maximizing power while minimizing weight. To achieve this incredible balance, birds have evolved a highly specialized skeleton. During evolution, many of their individual bones have fused together. This fusion provides the extreme rigidity needed to keep their body stiff during flight. Furthermore, the bones themselves are not solid like ours. They are hollow and filled with internal air spaces. We call these pneumatic bones. This structural genius ensures the bird remains incredibly light without sacrificing physical strength. Building on that lightweight skeleton, a bird still needs an engine powerful enough to lift it into the air. This engine comes in the form of massive pectoral muscles, which drive the powerful downward stroke of the wings. But muscles this large need a strong place to attach. Therefore, birds possess a highly specialized, enlarged breastbone, known as a keeled sternum. If you look at it, it resembles the deep keel on the bottom of a sailboat. This keel acts as the crucial anchor point for those enormous flight muscles. Without this deep anchor, the muscles would tear away from the bone under the immense forces of flapping. Together, the pneumatic bones and the keeled sternum create the perfect anatomical foundation for flight. Understanding this lightweight anatomy leads us to a key mathematical concept called wing loading. Think of wing loading like the pressure exerted by a shoe on the ground. A stiletto heel concentrates weight on a small area, while a snowshoe spreads it out. In the same way, a bird's wing must spread its body weight over enough surface area to push against the air and generate lift. The formula is W sub L equals M divided by A. Here, W sub L is the wing loading in kilograms per square meter. M stands for the total body mass of the bird in kilograms, and A represents the total surface area of the wings in square meters. If the mass increases without a change in wing area, the wing loading increases, meaning the bird must fly faster to stay airborne. Conversely, a larger wing area for a given mass decreases wing loading, allowing for slow, effortless gliding. Before we move on, let us see this formula in action with a concrete example. We want to calculate the wing loading for a common city pigeon. We are given that the pigeon has a body mass of 0.35 kilograms and a total wing area of 0.07 square meters. We need to find out how much mass is supported by each square meter of its wing. We substitute our given values into the formula, dividing 0.35 by 0.07. This straightforward division gives us a final wing loading of 5.0 kilograms per square meter. This is a relatively low wing loading, which physically means the pigeon has large wings compared to its overall body weight. This specific adaptation allows the pigeon to take off rapidly from the ground and maneuver easily through complex urban environments without stalling. Now that we have seen how wings support weight, we must address the energy required to flap them. Flapping wings requires an astonishing amount of energy, making flight the most metabolically demanding form of locomotion in the animal kingdom. To fuel this intense activity, a bird's respiratory and circulatory systems must be incredibly efficient at delivering oxygen to the muscles. Birds possess a unique system of air sacs connected to their lungs. This brilliant adaptation ensures that fresh, oxygen-rich air flows through the lungs continuously during both inhalation and exhalation. This constant supply of oxygen allows their massive flight muscles to burn fuel rapidly without fatiguing. This physiological marvel is exactly what sustains birds during long migrations across oceans and continents where resting is simply not an option. This incredible energy system powers the wings, but the shape of a bird's wing is just as important as its overall size. This shape dictates the bird's specific flight style, such as gliding versus rapid flapping. We measure this shape using a metric called the aspect ratio. Imagine comparing a long, thin glider airplane to a short, stubby fighter jet. The formula for aspect ratio is A sub r equals b squared divided by s. Here, A sub r is the aspect ratio, which is a pure dimensionless number. The symbol b stands for the wingspan, the distance from one wingtip to the other in meters. The symbol S represents the total surface area of the wings in square meters. When the wingspan increases significantly relative to the area, the aspect ratio becomes very high, resulting in long, narrow wings perfect for high-speed gliding. A low aspect ratio means short, broad wings ideal for quick takeoffs. Let us apply this formula to understand the flight of a wandering albatross. We are given a wingspan of 3.0 meters and a wing area of 0.6 square meters. We want to find its aspect ratio to understand its aerodynamic efficiency. First, we square the 3.0 meter wingspan, which gives us 9.0 square meters. Next, we divide this result by the wing area of 0.6 square meters. This mathematical operation quantifies the extreme length of the bird's wings relative to their total surface. The calculation yields a high aspect ratio of 15. This high number is a direct mathematical reflection of a wing built for sustained, energy-efficient soaring. It tells us exactly why the albatross is perfectly adapted for long-distance gliding over the open ocean, as these long, narrow wings drastically reduce aerodynamic drag at the wingtips. Now that we have seen a glider, let us calculate the aspect ratio for a common crow to see a very different flight style. The crow has a wingspan of 1.0 meters and a wing area of 0.2 square meters. Again, we start by squaring the wingspan. 1.0 squared is simply 1.0 square meters. We then divide this by the 0.2 square meter area. This calculation results in an aspect ratio of 5. Notice how much lower this is compared to the albatross. This lower number mathematically represents shorter, broader wings. The crow sacrifices the gliding efficiency of the albatross for the ability to maneuver quickly and take off rapidly in enclosed terrestrial environments. This perfectly illustrates how mathematical ratios in biology directly translate to an animal's survival strategy and ecological niche. Having calculated these ratios, let us visualize how they interact with the physical forces of flight. On screen, you see a diagram illustrating the four primary aerodynamic forces acting on a bird. Upward, we have lift, which must overcome the downward pull of gravity, or weight. Forward, we have thrust, generated by the flapping wings, which must overcome the backward resistance of aerodynamic drag. To the right, you can see the two wing shapes we just calculated. The long, slender wing at the top represents the high aspect ratio of our albatross, designed to maximize lift and minimize drag for gliding. The short, broad wing below represents the low aspect ratio of our crow, optimized for generating quick bursts of thrust and maneuvering. Every bird species balances these four forces differently depending on their unique wing geometry. We have covered a lot of ground today, so let us summarize the key takeaways. First, we learned that flight is a marvel of evolutionary engineering, requiring a streamlined body, specialized feathers, and a lightweight skeleton with hollow, pneumatic bones. Second, we used the wing loading formula to understand how a bird's mass and wing area dictate its agility and takeoff speed. Third, we explored the physiological marvel of avian air sacs, which provide the continuous oxygen needed to fuel massive flight muscles. Finally, we calculated the aspect ratio to see exactly how wing geometry determines whether a bird is built for soaring over oceans or darting through dense forests. You now have a solid mathematical and biological understanding of how birds have mastered the skies. Great job!